Okay, so here are the solutions to the 4 extra problems. So a pickup truck is carrying a toolbox, but the rear gate of the truck is missing. The toolbox will slide out if it is set moving. The coefficient of friction and the static friction between the box and the level bed of the truck are 0.355 and 0.650 respectively. Starting from rest, what is the shortest time this truck could accelerate uniformly to 30 meters per second without causing the box to slide? Okay, so let's draw a picture here. So you got a toolbox in here. And if you accelerate the truck too fast, then it's going to slide out the back. So what it's looking at is it's telling you the final velocity. And it's telling us the initial velocity. And then it's asking for time. So we only have two things. So what we've got to do is we've got to calculate the acceleration from Newton's second law, which then we can use to find the time. It's because then we'll have three things. Now, what will happen is that if this truck, if the box starts to slide, it'll continue to slide. So this just being the fact that it's less than that means that's going to happen. It's kind of like if you had a block on a ramp and it was stationary, but if you pushed it, once it starts moving at that particular angle, it's going to continue to accelerate because this kinetic coefficient of friction is less than static coefficient of friction. So really that's the only thing that is going to apply. Okay, so now what we're going to do is we're going to take that toolbox and we are going to draw a free body diagram on that thing. So we have the weight of the toolbox. Notice they didn't give us a weight, so it doesn't matter. The weight's not is going to be irrelevant. And we're going to have a friction force. And this friction force is the one determined by the static coefficient of friction. And then we're going to, what we're going to do is we are going to what are we going to do here? Because what'll happen is the actual truck bed will start to accelerate, which initially that would also cause the object to accelerate at the same rate as long as they're not sliding between each other. That's the acceleration is going to be the acceleration of the truck. So if we look at this free body diagram, we've got the normal force pushing up. That's the force that's holding the toolbox on the surface. We've got the weight going straight down, and then we've got the friction force pushing in this direction. And so this is the friction force. So if we look at the summation of forces in the x direction, which is the horizontal direction, we'll get mass times acceleration is equal to, now I've got the friction force pushing that way, but actually should it be the other way? It should actually be the other way. Because if we're going to accelerate this way, the friction force is going to be, I'm trying to remember, yeah, that's the question. Is the friction force going left or right? Actually, I think I was right initially. Because what's going to happen is that this thing wants to stay still, but the truck moves, so you're going to need a friction force to push it in the same direction as the truck. Okay, so that makes sense. Okay, so we have only one force acting on this. It's the friction force, which is in the positive x direction. And then in the y direction, we have some of the forces in the y direction. In this case, it equals 0 because it's a solid surface. And we've got the normal force pushing up, and we have the weight pushing down. So we get that the normal force is equal to the weight. We also have this relationship here, that the friction force is equal to the static coefficient of friction times the normal force. So I'm going to do this all algebraically. And also, the weight is the mass times acceleration due to gravity. So if we plug that in there, we'll get the normal force is the weight is mg, so you get US mg. Static coefficient of friction, the mass, the acceleration due to gravity. And we can stick that in here for the friction force. And then you can see we have masses in each term, and so the acceleration is just the static coefficient of friction times g. So what it's saying is that if the acceleration is greater than this, then the friction force is not sufficient to keep it from sliding. So we don't need to know the mass, we just need to know the static coefficient of friction and the acceleration due to gravity. So we got the static coefficient of friction is given in the problem, 0.355, which is unitless, times g, which is 9.81 meters per second squared, and you get the answer. Oh, we get the acceleration. We still haven't answered the question yet. We get 3.48. So that's limiting acceleration. So if we go up here and put that in here, 3.48 meters per second squared, then we need an equation to solve for t given these three things. So we have v is equal to v0 plus at. v0 is 0. If you solve for t, you'll get v over a. So v is 30 meters per second. A is 3.48 meters per second squared, which gives us the answer, which is 30 divided by 3.48, which is 8.6 seconds. So if we took less time than 8.6 seconds, then our acceleration will be greater than 3.48 meters per second squared. And as a consequence, this thing would start to slide. As I said, once it starts to slide at that given acceleration, then it's going to keep sliding and it'll go off the end of the truck. Okay, the next three problems are like we've done before, but they're asking it in a different direction. You know, in the ones we've done, we've given you the masses, we've given you coefficient of frictions, things like that. Here, they're asking us to figure out other things, but it's the same basic equations that we've had before. But let's read it. Okay, so as shown in the figure, block A, 2.25 kilograms, rests on a tabletop. It's connected by a horizontal cord passing over a light frictionless pulley to a hanging block B. The coefficient of friction between A and the tabletop is 0.45, and that's kinetic. You see it's kinetic. The blocks are released then from rest. Draw one or more free body diagrams to find A, the speed of each block after they move 3 centimeters, and the tension in the cord. So what they want us to do is calculate the acceleration, which is actually pretty simple. It's similar to what we've done before. Then we use that acceleration and the fact that the initial velocity is 0 and that the distance is 3 centimeters, we then can calculate final velocity and time if they'd asked that from us. And then once we know the acceleration, we can also calculate the tension. We could do that before A. Okay, so it's actually a simpler version of what we've done in the past. We've got two free body diagrams. Here we have the tension pulling up. We have the weight pulling down. We'll call that W sub B, which is M sub B times G. Then we have pulling here, we have tension. We have the weight, W sub A, which is M sub A times G. We have friction, which is the opposite, the direction of motion. So it's going to the left since the motion is to the right. We have our normal force pushing upward. And that's pretty much it. And what else can we say? These are coordinate systems, so we'll have x go to the right, y go up. Here we'll have y go up, x to the right. So we have to apply Newton's second law to both of these scenarios. Now, in the x direction we have movement, so we have acceleration. I'm going to use a sub x, a, x direction for object A, mass A. Okay, we have two forces. We have the tension pulling to the right, which is positive x. We have the friction force pushing to the left, which is negative. So that is it. When we did the inclined plane, we had another term, which was the x component of the weight, but in this case there is no x component of weight because it's all horizontal. Then we have the sum of the forces in the y direction. It's equal to 0 because it's a solid surface. And we have the normal force pushing up and the weight pushing down. What else do we know about this one? We know that the the friction force is equal to the kinetic coefficient of friction times the normal force. And I think that's it. Over here, there's nothing going on in the x direction. There's no forces, there's no movement. And then here we have, let's put a subscript A again. Okay, so in the y direction we do have movement. So that's m sub b times a sub y b. And we got two forces. We got the tension pulling up and we have the weight pulling down. And we don't have any friction, so it comes down to basically this equation. And like we've done in all these problems, ultimately we want to get this equation so that the only unknowns are the acceleration and the tension. And then we want this one so that the only unknowns are the acceleration and the tension. The tensions are the same. So we could call this TA, we could call this T sub B, but because the wheel is frictionless and massless, the tensions are equal to each other. So we're just going to call that T ultimately. And what else do we have to say? I think that's it. And I'm going to have to make a little room in here. Now I could do all this algebraically, but I'm not going to. So let's calculate the weights. So we've got 2.25 and 1.3. I already did that wrong. 2.25. Oh, no, I did that right. G, 9.81. Over here, we've got 1.3. Okay, so get our calculator out. 25 times 9.81 is 22.1 newtons. Over here we have 1.3 times 9.81, which is 12.8 newtons. Okay, so those are the weights. So from this equation, we know that the normal force is equal to the weight. But the weight is 22.1 newtons. So that's F sub n, the normal force. Then we can calculate the friction force. So we have a kinetic coefficient of friction of 0.45 times the normal force, which is 22.1. 9.95 newtons. And hopefully that is going to be greater than or less than this hanging weight. If not, it wouldn't move. So it is, so we're in good shape. Okay. Now we're going to be able to substitute that in here. We know the mass. We know W sub B. We know M sub B, so we can do the substitutions and end up with two equations and two unknowns. The only thing is our acceleration, so we got to get the sign right. So you can see positive x, which is left to right, means it's going to go down. So we go to this thing. So this move some positive x direction. This will go down, which is in the negative y direction. So what we can say is a sub xa is equal to negative a sub y b, and we'll just call that a. Okay, so now we're going to plug in to the two equations. So we have m sub a, just write this out, m sub a sub x sub a is equal to t. I just replace t sub a with t, friction force of a. Okay, so the mass of a is 2.25 kilograms. A sub xa is equal to a, t minus the friction force, which is 9.95. So that's one equation. And the second equation, this one here, which says m sub b a sub yb is equal to t, instead of t sub b, minus w sub b. So mb is equal to 1.3 times negative a, because this is negative, so it's negative a, is equal to t minus w sub b, which is 12.8 right there. So two equations, two unknowns. We're going to solve for t, so let's solve this one for t. So it'll be 2.25a plus 9.95. So we move this to the other side. Over here we have negative 1.3a is equal to t minus 12.8. So if we then substitute it here, we'll get negative 1.3a is equal to t, which is 2.25a plus 9.95 minus 12.8. So this is t in terms of a. Plug that in there. So if we subtract 2.25 from both sides and combine the terms, we'll get we'll get negative 3.55 A, and then we have 9.95 minus 12.8, which is negative 2.85. And if you solve for A, you'll get an acceleration of plus 0.803 meters per second squared. Okay, so that's the acceleration. Now, if we had done this algebraically, what the equation would look like is the acceleration is equal to, well, we'd have the sum of the two masses. That's the inertia, total inertia. We'd have the we'd have G times the difference in the masses. Well, actually, no. What we would have is, if we wanted to make this thing go as fast as possible, we'd have zero friction. And what would cause that to happen is that we would have the weight, which would be m sub b times g. So that's the weight of b. So that's going to pull it down, things down. And then we have this friction force, which is equal to the kinetic coefficient of friction times m sub a times g. So the friction is going to slow things down. And the bigger the coefficient of friction, the more it's going to be slowed down. So if we plug the same numbers in here, we should get the same answer. Just to double check here. So m sub b is 1.3, 9.8 minus the coefficient of friction, which is 0.45, times m sub a, which is 2.25, times g, which is 9.81, all divided by 1.3 plus 2.25. Okay, so hopefully this works out. Of course, I could do this because I've done the bazillion of them. I just wanted to do this to show you that kind of how the equation comes out. We're doing these kind of things in our lab, so. Okay, and what I get is 0.795. Okay, so it's just some rounding off issues here, but you can see they're the same number. Okay, so that's the acceleration. So now find the speed of each block after they move 3 centimeters. So this is a constant acceleration problem with v0 equal to 0. We don't know v. We do know that delta x is equal to 0.30 meters, I think, or is it 0.03 meters? 3 centimeters. Okay, so it's 0.03. And what else do we know? Oh, the acceleration is 0.8. We'll take the first number. 0.803 meters per second squared. And what we want to know is find the speed of each block. Okay, so speed is velocity. So we want v. So which equation uses that? Well, it's the fourth one. V squared is equal to v0 squared plus 2a delta x. With v0 equal to 0, so you get v squared is equal to 2 times acceleration, which is 0.803 meters per second squared, times delta x, which is 0.03 meters. And we get 2 times 0.803 times 0.03. So it's 0.0408 meters squared per second squared, and then we take the square root, and we get 0.22 meters per second. And it's positive because it's moving from left to right. Okay, so that's the velocity, and that's the velocity of both of them because they're connected together. And then finally, to calculate the tension, all we have to do is go up to this equation. So tension is equal to 2.25 times 0.0803 plus 9.95. So 2.25 times 0.803 plus 9.95 is equal to 11.8 newtons. So, if there was no acceleration, the tension would be just trying to make sure I'm thinking about this right. Actually, what the tension would be 12.8 if things are stationary. But because things are falling, the tension is a little bit less. So this part here, this tension here is the same as tension there. If this were stationary, the tension would be equal to the weight of the object. But because this thing's falling, it's going to be less than 12.8, which is 11.8. So it's slightly less tension. Okay, let's do the third problem. This one is actually more of a way to explain how pulleys work. So it asks us to draw one or more free body diagrams to find the tension in each chain and the magnitude F in terms of weight W. If the weight is lifted at constant speed, what that means is there's no acceleration. So it's almost like an equilibrium problem. Okay, so what happens is we pull down on this rope with certain force. So that results in a tension in this rope. Now, we assume that the pulleys have negligible weight and there's no friction. So that means the tension in this pulley, side of the pulley is the same, and the tension in that pulley is the same. So they all see this force F pull down. So if you look at, let's call this A and B. So if we draw a circle for A, you've got T pulling up here, and you've got T pulling up here, and pulling downward is the weight. And because these things are moving at constant velocity, or just the instant just before, if they pulled on it really slowly, we wouldn't have, like I said, we wouldn't have to worry about the acceleration of anything. So if you sum the forces in the y direction, it's going to be equal to 0, because the acceleration is 0, constant speed. So what we have is we have the two tensions pulling upward and the weight pulling downward, and that has to equal to 0. So the weight is equal to 2t, or the tension is equal to W over 2. Likewise over here for this second pulley, the one that's on the right, we're pulling down with force F on both sides, or we're actually pulling down with this tension T. And so the force that's pulling up from this hanger is equal to some tension. We'll call it Y. So you can see Y is going to be equal to 2t again, because the sum of the forces in the y direction have to be equal to 0, So we have the tension pulling down both places. And in this case, as far as the rope over here, this is the only force this sees is the tension in the cable, which is half the weight, or half the force. So pulling down, we have the weight, which is supported by these two ropes, one that's fixed and one that's moving. So that, like I said, this one that's fixed is going to have a tension of half the weight. This one's going to have half the weight. This one's going to have half the weight. So ultimately what that means is that I only have to pull with half the force, half the value of the weight to lift this weight up. So if I were to just pick up a weight, the tension would be equal to the weight without a pulley, because you'd have the weight pulling down and you'd have to pull it all up, pull it just by one rope, which would have to be the same, the tension. So the advantage of the pulley, two things is, one is the tension that you have to pull on the rope is going to be half. The other advantage is, in this case, you can use your weight of your body to pull down this way, which is going to lift the weight up that way. If you have to do it this way, you'd have to be pulling it up with your back. It would be a real pain in the neck. So there's a whole bunch of advantages of pulleys. Now, if you have more than two pulleys, if you had 4 pulleys, so the way that would work is you'd have a pulley here, which would go up to another pulley here, which would be supported. So these are all supported. Then it would go down to another pulley this way, which would be, I guess you'd have to have it pulled this way, attached to the floor. Then you go up this way and then another pulley, and then you would pull on it like that. So this would have to have connected to the ceiling. So, and then this would be attached to some kind of weight. So you'd pull on this rope. Each one of these would have a tension. Actually, that's not the way it works. That doesn't really help you a whole lot doing in that configuration. So what happens is you kind of put these in line. So instead of this way, you kind of align them in the backward direction. And ultimately what you have is you have 4 ropes. So you kind of you have to look at it from the side perspective. Here and here you'd have 2 pulleys. And the rope would loop over like that, and then this one would go around and loop over that one. And if you have 4 pulleys, then you only have to pull with 1/4 of the force. Now the thing that's tricky is that you have to pull this one twice as far. If you wanted to lift this 1 meter like that, you would have to move this force through 2 meters. So it's nothing's free. You still have to do the same amount of work in all these situations. It's just you're able to reduce the amount of force needed to lift the weight. And like I said, you just have to pull the rope further to accomplish the same task. The task involves lifting the weight through a distance, not just lifting the weight. Okay, so here's our last problem. So we have a mass M1, 20 kilograms, angle 53.1 degrees. The kinetic coefficient of friction is 0.4. What must be the mass M2 of the hanging block be if it is to descend 12 meters in the first 3 seconds after the system is released from rest? So in the previous problems, we calculated the acceleration, and then we used that to back out the other unknowns. In this case, we're going to use these 3 things to calculate the acceleration, and then we'll use the acceleration to back out what M2 needs to be to cause that acceleration. So we're going to start with the one-dimensional equations first, and what we know is we know delta y, that's this distance, is going to be equal to V0 t, no, that's not the one I want to use. I was going to say, what do I know? I'm getting a little ahead of myself here. So I know delta y, I know t, and I know v0. And what I'm trying to find is the acceleration. So which one of those equations could I use to solve for a? And I think it's the third one. Delta y is equal to v0t plus 1/2 at squared. This is 0. So if you solve for the acceleration, you'll get 2 delta y over t squared. So we multiply both sides by 2, divide both sides by t squared. So you get 2 times delta y, which is 12 meters, divided by 3 seconds squared. So to achieve that end goal here, we have to have an acceleration of 2.67 meters per second squared, which is good because this number has to be less than 9.8 or it's not going to work out. Okay, so now we know the acceleration. And so we're going to draw our free body diagrams for the two objects. Define our coordinate systems here. The forces acting on this are the tension, the weight, the normal force, and the friction force. Down here we have, or to the right, we have the tension and we have the weight. And let's go ahead and put some subscripts in here. We'll call this, oh, this is object 1, so we'll put a 1. So this is friction force 1, this is normal force 1, weight 1. T we don't need to put, we could, we don't need to because it's the same. Here we got W2. Now what we'll do is we'll replace this weight with the components. So we'll have W sub x1 and we'll have W sub y1. Mark through that one there. So let's make our free body diagram. Here's our point. Here's the tension. Here's my coordinate system. Here's the normal force. Here's the y component of the weight. Here is the friction force. Here is the x component of the weight. And we know that the weight, W1, let's put some subscripts again. W1 equals M1G. W2 equals M2G. And that's what we're trying to solve for. We're trying to figure out what the mass of the second thing. So this is what we're solving for, ultimately. Okay, so W1 is M1G. W1X is W1 times the cosine of the sine. Why is it the sine? Because here's the angle theta or alpha. It's the opposite side, W sub x. So it's going to be times the sine of, what do we use? They used alpha, I think. Alpha. Sine of alpha. W1y is W1 cosine of alpha. Okay, so we got all the W stuff. We know the friction force is equal to the coefficient of friction times the normal force. Okay, so let's do Newton's laws here. So the sum of the forces in the x direction for object 1 is equal to M1 m1a sub x1. And if we look at our diagram, we've got tensions pulling in the positive direction, the friction forces in the negative direction, the W sub x1 is in the negative direction. So that is the sum of the forces in the x direction, and then we have the sum of the forces in the y direction, which is 0 because it's a solid surface. And we've got the normal force minus the y component of the weight. So that's what we get out of there. And then over here, we don't really have anything going on the x direction. We just have y direction. It is moving, m2a sub y2. And we've got y going up, so it's going to be t minus w2. Ultimately, if we solve for w2, then we can solve for m2. So I think we're going to try to solve for that. Now we already know the acceleration, so this will be actually pretty easy. What we'll be able to do, let me just kind of talk you through what we'll do. We don't have to solve any. We'll be able to solve this equation for the tension, and then we can use that tension here with the acceleration and the mass to work it out. Now let's take this number and make sure we have the signs correct. So it's going to be going up the ramp. I think it said that. Oh, actually yeah. So this is descending. Hanging block is descending, so we know that's going up. So what we can say here is that a sub x1 is positive 2.67 meters per second squared, and a sub y2 is negative 2.67 meters per second squared, because it's going, m2 is going down, which is opposite the positively defined y. Okay, so we got that. So I think all we have to do is just plug everything in and just work our way through this thing. So we're going to use this equation. So what's m1? m1 is 20 kilograms. I'm leaving off the units just to make it a little easier to deal with. A sub x1 is positive 2.67. All right, I was going to leave the units off, then I stick them on. Let's just leave them off for right now. Is equal to T minus the friction force. So the way we do that is from here, we know that normal force is equal to W sub Y1. So we need to calculate these things. We haven't done that yet. Actually, we haven't done W1 yet. Let's go back all the way back up here. So that's 20 kilograms times 9.8. 20 times 9.8. 196 newtons. Okay, then we have the components. 196 newtons times the sine of, what is it, 53.1 degrees. Okay, 51, was it? 51.3 or 53.1. That sounded like I did it wrong. Okay, 53.1. And the y component is 196 times the cosine of 53.1 degrees. So make sure calculators in degrees. You got to be careful because in calculus we tend to use radians. So it depends on when we've used our calculator last. Okay, so the x component is 157 newtons. And the y component is 118 newtons. Okay, so those are the components of the weight. And what we know is that The normal force is equal to the y component of the weight, and therefore the friction force is the friction coefficient, which is given in the problem as 0.4 times normal force, which is 118, which is 47.2 newtons. Okay, so that's that. So now we can stick it in. We were just getting to that point. Okay, so we're going to subtract the friction force, 47.2, and we're going to subtract the x component of the weight, which is 157. So you can see the only unknown here is the tension. So we'll have 20. If we solve for this, we'll get T is equal to, well, if you multiply 20 times 2.67, this is 53.4. So we got 53.4 plus 47.2 plus 157. Notice they're all plus. We'll talk about that in just a second. So we get 250. I'm going to carry an extra decimal point here. Actually, maybe two extra ones. But okay, so that's the tension. Why is it? Why do these all contribute to the tension? Okay, so this one is because you're accelerating. You know, if you have something and you pull on it like that and you accelerate it, you're going to create a tension in that cable. Okay, so just the process of pulling something. So that's that one. The second one is the friction force. That's because if you're pulling on something, you're going to get a force in the opposite direction because of friction. And then the third part is this x component of the weight, because you're going down the ramp here. It's wanting to pull this down the ramp. So all those three contribute to a tension. You need a tension to overcome all three of those. Well, actually, what you're doing is these two. This one is because of the mass of the object. This one is due to the friction force because it's moving, and this one is because of the inertia of the object. If you're on a flat surface, this part would be 0. If you were frictionless, this would be 0. If you weren't accelerating, both of these would be 0. If you weren't moving, if you're stationary, these both would be 0. If you were moving at constant velocity, this would be 0. Okay, you may have to go back and listen to that and think about it. Okay, so there's the tension. So now what you can do is you can go over here, and what we're trying to do is calculate M. Well, actually M is part of both of those. So you've got M times A sub y2 is equal to T. W2 is M2G. I guess I can go ahead and put that in because I've already calculated it, I think. Did I? Well, no, actually I haven't calculated that. So this is M2G. So if we move these both to the same side, you'll get M2A sub x2 plus M2G is equal to T. And then if you factor out, let's go down here, factor out a M2, you get M2 times A sub y2 plus sub y times G equals T, or M2 is equal to T divided by A sub y2 plus G. So we know the tension. We calculated that up here, 257.6. The acceleration of object 2 is negative because it's going down. So it's accelerating downward, which is negative. So you're going to get negative 2.67 meters per second. And then you have plus G, which is 9.81. And then we get the answer. So I get mass 2 is 20.6 kilograms. And again, you can see what's going on here. If you're not accelerating, acceleration is 0. The tension in the well, you'd have to also set acceleration equal to 0 over here. So anyway, that's the answer. 20.6 kilograms. Is that all they asked for? What must be the mass M2 of the hanging block if it is to descend 12 meters in 3 seconds? So let's kind of review what we did here. We used the one-dimensional equations to calculate the acceleration to satisfy these 3 requirements: change in displacement, time, and initial velocity. So we got 2.67 meters per second squared. As far as these specific objects, object 1 and object 2, the acceleration here is up the ramp. So that's positive 2.67. And this one's falling down at the same rate, except it's a negative because it's going negative y, whereas positive y is directed upward. Then we look at the forces. And we got the tension, the weight, the friction force, the normal force. We break the weight into the 2 components, W sub x1, W1x and W1y. Just use the geometry of this triangle here where the x component is opposite the angle. So it's the sine. W1y is cosine. You find W1 just by taking the mass of object 1 times g. So these are your components of the mass, parallel and perpendicular to the solid surface. So we can put all the forces in here in this diagram. Tension pulling in the positive x direction, the friction and the weight component, x component weight going down. We've got the y component of weight balanced by the normal force. It has to be balanced because there's no acceleration in the y direction. So then if we apply Newton's second law in the x direction, it is moving in the x direction, so we include this acceleration. We've got the tension pulling positive, friction and x component of weight negative. Likewise, for the falling object, we've got the tension pulling up, the weight pulling down. So you end up with this equation. There's no angles because it's just going straight up and down, and the axes are straight up and down. In this case, unlike previous problems where we have the acceleration given to us and we have to calculate something else, and that something else ends up being what is the mass M2. So we're able to use all the information that's given to solve for the tension in the cable from this equation. And then we can use that tension plus knowing what the acceleration of object y is and what the acceleration due to gravity is. The only other known is m2, so we can solve that algebraically. Plug the numbers in, get the answer. So that is it for those.